Okay, so now we are ready to talk about sort of general purpose neural nets, but let me start again with the logistic regression framework. So remember, in multi-class logistic regression, you had a softmax on top, which was spitting out your y hat, which is these estimated sort of class probabilities. What was coming in are your sort of the LLR models that you have. Let me call it Z for now. And how was Z obtained? It was obtained by basically a linear model operating on a feature vector phi, and presumably somebody told you how to figure out the feature vector from the input, right? So we, for example, it's either implicit or explicit. Let's think of it as explicit right now. You basically figured out what kind of terms you want. Maybe you take the linear and quadratic terms and add a constant for the biases. Whatever you do, there's some feature vector that you compute, and then you train the weights. Train the weights to basically optimize some cost function by comparing this with the labels. So the labels are given, and basically there is the standard term that is used a lot in the neural net literature is a loss function. So I'm going to say a loss function that compares the labels with the estimates, and these are, I'm assuming, one hot labeling here, and then basically you optimize this to train your weights. So that's sort of the framework for multi-class logistic regression that is there in the previous handout. And just to label some of the dimensions here, we were thinking of X as a D cross 1 vector, phi as a capital D cross 1 vector. Of course, there are K classes, so this is Z is K cross 1, and Y hat is also K cross 1. So that was the setup. So now we are going to replace the feature extraction box, this box, by a neural network, right? So there is this last layer where here that we were training. This one was coming after the feature extractor, but now we'll train the feature extractor as well. So let me change my pen color and train this as well. So we'll basically have a bunch of weights, some corresponding to the neural network, and the last layer will also be considered part of the neural network, right? So that's the setup. Okay, so what does a general purpose neural network look like? So let me draw the picture. You have the input coming in at, let me try it from the bottom. The input is coming in here. I am going to put it through one layer of neurons, and basically I'm going to call it layer 1. The weights are going to be W1, the bias is going to be B1, and then I'm going to pass it through a nonlinearity. These nonlinearities could be layer dependent, but I'm going to use the same form psi for all of them. And this is the output of the first hidden layer, right? And the input can be thought of, okay, so I'm going to keep it that way. And then the next layer will look exactly the same thing. The dimensions can be different for all these quantities. There's the weights, the biases, and then out comes that, again going through a nonlinearity, and so on. I'm going to have to draw out the whole picture more compactly, but let's first see what write out what this looks like a bit better. So right on the side here. So let me change my pen color and see what this looks like. So basically I have these d-dimensional input, x1 through xd. These are scalars coming in, and I'm going to multiply them by these weights, right? So and then I'm going to pass it through a nonlinearity, and I'm going to do the same for all these neurons. Nonlinearity, weights, up to something, right? So basically I might have, say, n1 neurons in this first layer, and this might be the ith neuron, so the ith neuron, and basically what I want is what's coming into the ith neuron is wij plus a bias that depends on the ith neuron. I'm not showing the bias in this picture, and then pass through the nonlinearity, and then that gives me the output of this ith neuron. So I need to make up some notation here as well. So what this output is the output of this first hidden layer. So the ith output of the first hidden layer. So this is my hi of 1. This is what comes out of the ith neuron in the first hidden layer. So I is going from 1 through n1, right? I also would like to define an intermediate variable before I applied the nonlinearities. And actually you do that in your computation also. You actually do this computation. And let me call it as the activation of the ith neuron before the nonlinearities. So, I can call it presynaptic or whatever, but it doesn't matter. Let me just label these AIs, right? So that's sort of the notation I have. And this wij, of course, is for the first layer, the bi is for the first layer, etc. And as I go proceed upwards through the layers, I'll have that for the the kth layer, layer k, the ith neuron there, and this is of course a completely different I, is I forgot to put the summation here. This is summation over j, right? J equals 1 to d, right? There was a summation of the inputs coming, the weighted inputs from all these guys. So here also you'll have a summation, j equals 1 to, and we'll figure out what that is, wij k for the kth layer times the output from the jth guy in the k minus 1th layer plus bi k. And now I will be going from 1 to however many neurons there are in the kth layer. Let's call it nk. And the summation j is going from however many layers there are, neurons there are in the k minus 1th layer, nk minus 1. So that's how sort of things proceed upward as I'm heading towards the softmax. So let me write this out in matrix form. I'm going to define these intermediate activation variables that are linear functions of the previous layer outputs. So AK is WK times HK minus 1 plus BK. This is what comes of collecting the previous equations. Let me change pen color to show you. Essentially, this part, these equations, I mean, this business is what I'm calling AIK, and AK just collects all of these into one vector. So let me write that down. A1K down to A sub NKK, right? That's your these sort of linear transformation of the previous layer. And then, of course, the output comes after the nonlinearity. So HK is just term by term nonlinearity applied to these so-called, let me name these, pre-synaptic activations. And these are sort of post-synaptic. This is synapses coming from, the term comes from neuroscience. These are not really like real neurons, how real neurons work, but we'll adopt these terms sometimes just to avoid talking about A's and H's. So that's what we have in terms of the generic kth layer. So let me redraw the picture, but now I'm going to make sure I have enough room. So I'm going to start from the top. So the top, let's assume we are doing a classification problem. So the top is a softmax, and out comes the y hat from there, and then that comes from, and let me just think of these as the weights and biases corresponding to the last layer. I'm just calling it M. And after that, the picture becomes more sort of unified. So basically, I might have these nonlinearities, term by term nonlinearities that might be layer dependent, but I am not going to put that in the notation. So I have these M layers, and I have this kind of picture. I'm going to keep going like this. This also comes from a nonlinearity, term by term, and I keep going down to the first layer, first hidden layer, which was described by W1 and B1. And there the input was X, right? So this has become a pretty big figure that barely fits on the screen. So you can see that I'm having to move it around to do this. And the notation we have is that the output of a given layer after the nonlinearity is called H, and the one before is called A. And I'm going to just change pen color and say, okay, for the kth layer out here, some generic kth layer, my picture is WK, BK, psi, giving me HK, and what's coming in here is K minus 1. So that's the picture we have, and here the output, of course, is AK. And the equation we had before still stands. I have AK is WK HK minus 1 plus BK, and HK is the term-by-term application of the nonlinearities to these AKs, and this picture, this holds from K going from 1 through M, as long as you are willing to define the input as the output of a sort of zeroth hidden layer, right? So that's the overall picture. And now we have to learn to train all these weights and biases over the entire network. So just like in logistic regression, what you're going to be training is the cross entropy loss function generically, right? So let's talk about that. So what are we going to be training for? So we'll train to minimize a loss function, and what it and I'm going to switch to the notation that is most common. Capital L is used for the loss function. It's basically equal to the cross entropy loss function that we saw before. It's basically how well the y hats and the y's are matching using graph, plus regularization terms. And regularization, remember what we took was of the L2 norm squared of the weights for the logistic regression, and that's exactly what we are going to take again. We're just going to regularize all the weights there. Basically Wi, J for all layers. I'm going to square those, sum over I, J, and layers, and then there's going to be some lambda over 2 term that basically says how much you are caring about this regularization. And the cross entropy picture is exactly the same. I guess I can denote this as little l of y and y hat, and changing pen colors. This is can be summed over training examples, right? That's what we had. So what and how did we deal with it? We actually, for logistic regression, we used the Newton method that used both the gradient and the Hessian of the loss function with respect to the weights, and that converges rather quickly. When you're talking about a very large network with a very large number of weights, computing the Hessian is out of the question, so you simply use gradient descent. So for a generic weight or bias, you basically say something like, weight new is weight old minus the derivative of the loss function with respect to the weight evaluated at weight old times some number, and this number is typically small. You take small steps along the gradient, so you don't sort of oscillate too much, and it's called the learning rate. This eta is called the learning rate, and you do the same thing for biases also, right? So the question now is, how do you? The main question now is, how do I compute this guy? Remember that there's a huge number of weights there, and there are different sort of distances away from the output. This loss function, the cross entropy is based on just the final output y hat, and I might be looking at a weight 10 layers down from it. How do I compute this guy? And this is where backpropagation comes in, which is just an application of the chain rule of differentiation over and over again.